This video is on composite and inverse functions, and we'll start with composite functions. Let's say we have two functions, f of x, which is equal to 2x plus 3, and g of x, which is equal to 5x plus 7. The composite function fg of x means that we replace every x in f of x with a g of x. Another way to write this is f of g of x like this, where it's f of x but the x is replaced with a g of x. So fg of x is equal to, so f of x is 2x plus 3, so it's going to be 2, but we replace the f with g of x, 5x plus 7, so it's going to be 2 of 5x plus 7 plus 3. If we expand the brackets, it's going to be 10x plus 14 plus 3, which is equal to 10x plus 17. So fg of x is equal to 10x plus 17. And if we need to find fg of 3, we would just plug 3 in as x into this function. So it would be equal to 10 of 3 plus 17, which is equal to 30 plus 17, which is equal to 47. So fg of 3 is equal to 47. If we had to do the opposite, if we had to find the composite function g f of x, this means that we will replace every x in g of x with f of x. Again, another way to write this is g of f of x like this. So g f of x would be equal to, so g of x is 5x plus 7, so it would be 5, but we replace x with 2x plus 3. So it would be 5 of 2x plus 3 plus 7, expand the brackets to 10x plus 15 plus 7, which is equal to 10x plus 22. And then if we needed to find gf of 3, we just sub 3 into here, so it becomes 10 of 3 plus 22, which is equal to 30 plus 22, which is equal to 52. So gf of 3 is equal to 52. If we needed to find f of x, this is where we replace every x in f of x with another f of x. Another way this could be written is f squared x like this, where we kind of combine the two f's into f squared. So f of x is going to be, so f of x is 2x plus 3, so it's going to be 2, but we replace the x with another 2x plus 3, so it's going to be 2 of 2x plus 3 plus 3. If we expand the brackets, it's going to be 4x plus 6 plus 3, which is going to be 4x plus 9. So f of x, or another thing it could be written as, is f squared x is equal to 4x plus 9. So here's an exam style question they could ask you. It's quite common to do, for composite functions, to do e to the power of x and the natural logs of x, because they simplify down quite easily, as we'll see. So for part A, we need to find fg of 5. So the first thing we need to do is find fg of x. So this means that it's going to be f of x, but we replace every single x with g of x. So this is going to be equal to e to the power of 4, and then we replace x with g of x, half natural log of x. So it's going to be e to the power of 4 half natural log of x, and then plus 1, which is going to be equal to e to the power of 4 times a half is 2, so it's going to be 2 natural log of x plus 1, which can be written as e to the power of the natural log of x squared plus 1. And then if you recall back to the laws of logarithm video, when we have e to the power of the natural log of x squared, this would just be equal to x squared plus 1. So fg of x is equal to x squared plus 1. So that means that fg of 5 is equal to, and we sub 5 in as x. So it's going to be equal to 5 squared plus 1, which is equal to 26. And then for part B, we need to solve the equation fg of x is equal to 2, and we found out from before that fg of x is equal to x squared plus 1, so therefore x squared plus 1 would be equal to 2, and then put 1 onto the other side to do x squared is equal to 1, so therefore x is equal to plus or minus 1. But remember that we've got the natural log of x here, and x therefore cannot be equal to minus 1, because you can't natural log a negative number, so therefore x is just equal to 1, and that's the only solution. So here's another quite typical exam question. I've seen this before where they want you to equal fg of x to gf of x and then solve the equation. So first of all, we need to find fg of x and gf of x. So fg of x will be equal to, so we replace for fg of x, replace every single value of x in f of x with g of x. So x squared plus 9 is going to become 3x squared plus 9, which is going to be equal to 9x squared plus 9. So that's fg of x, and then gf of x is going to be 3x here, but replace every single value of x with x squared plus 9. So gf of x is going to be equal to 3 of x squared plus 9, which is equal to 3x squared plus 27. And then what we do is equal these to each other and then find the set of values that satisfy that. So it's going to be 9x squared plus 9 is equal to 3x squared plus 27. Move the 9 onto the other side to do 9x squared is equal to 3x squared plus 18, and then move the 3x onto the other side to do 6x squared is equal to 18, and divide both sides by 6 to get x squared is equal to 3. So therefore x is going to be equal to the square root of 3, so it's going to be plus or minus root 3. So those are the two values of x that satisfy the equation when x is equal to plus or minus root 3. Now let's move on to inverses. So a normal function converts an input into an output. An inverse does the opposite. It converts the output into the input. So how do we find an inverse? Well, let's say that we had a function f of x, and let's say that f of x was equal to 5x minus 4, and we wanted to find the inverse of this function. Well, the first thing that we do is we replace f of x with y, so this has become y is equal to 5x minus 4, and then we rearrange this in order to make x the subject of the equation. So move the minus 4 onto the other side to do y plus 4 is equal to 5x, and then divide both sides by 5 to get y plus 4 over 5 is equal to x. And then finally, you just replace the y here with an x, and you kind of ignore this side here. So this would become x plus 4 over 5. And this is the inverse. F of minus 1 of x is equal to this, x plus 4 over 5. We call the inverse f of minus 1. We've seen calling inverses like this before in trig, for example, when we say the inverse of sin of x is equal to sin of minus 1 of x. And we can see that it's the inverse based on this up here. By putting any input into f of x, I'm just going to put in 2. So we do f of 2, and this is equal to 5, this function here, 5 2 minus 4, which is equal to 10 minus 4, which is equal to 6. So this is the output, and then we put this output into the inverse, so it's going to be f of minus 1 of 6, which is going to be equal to this function here, which is 6 plus 4 over 5, which is equal to 10 over 5, which is equal to 2, and 2 is the original input that we put in at the start. So the inverse converts the output back into the input. So just a couple of other notes with inverses. Firstly, whatever the domain and range is of f of x, it switches around for the inverse f of minus 1 of x. So for example, let's say the domain of this function was between 0 and 5, and it could still equal these as well. And if you figured it out, the range of f of x here would be equal to, or be between minus 4 and 21. We talked about how to find ranges in the more on functions video. So for the inverse, the domain would be the range of f of x. So the domain would be minus 4, between minus 4 and 21, and the range would be the domain of f of x. So the range would be between 0 and 5. So these are the set of values of x that you can put in, and these are the possible values that you could put out. Another feature of inverses is that if you do the composite function f of minus 1 of x, firstly, this would be also equal to the composite function f of minus 1 of f of x. But with both of these, the f's kind of cancel out, and whatever the answer is what is left in the bracket. So both of these would just be equal to x, whatever is left in the bracket. And this is the case for whatever the value of x is, or whatever the function is f of x. So for example, if we had something like f of minus 1 of 3, no matter what the function is, the answer would be whatever is in the bracket, as these two kind of cancel out. So this would be equal to 3. We can see this for our example with f of x and f of minus 1 of x. If we do the composite function f of minus 1 of x, this would be equal to 5, and then we replace x with x plus 4 over 5, f of minus 1, so this would be 5 of x plus 4 over 5, and then the minus 4, which is going to be equal to the 5's, the denominator cancels out to give x plus 4 minus 4, and this is just equal to x, which is what's in the bracket. So here's an example where we have f of x is equal to 3x squared plus 2, where x is bigger than or equal to 0, and we need to find the inverse. So the first thing that we did, as before, is replace f of x with y, so it's y is equal to 3x squared plus 2, and then we make x the subject of the equation. So move 2 onto the other side to do y minus 2 is equal to 3x squared, and divide both sides by 3 to get y minus 2 divided by 3 is equal to x squared. So therefore x is going to be equal to the square root of y minus 2 over 3. You might be tempted to say that it could be equal to plus or minus the square root of this. I'll talk about this a bit more in a sec, but this is not the case, because if it was the plus or minus, as we talked about in the more on functions video, this would then become a one-to-many function mapping, which by definition is not a function. We'll talk about a bit more in a sec technically why this is, but this is why we don't want it to be plus or minus the square root. And then what we just do is replace the y with the x, so it becomes the square root of x minus 2 over 3. And then this is the inverse. F of minus 1 of x is equal to the square root of x minus 2 over 3. We also need to find the domain and range of f of minus 1 of x. So first of all, let's start with f of x. The domain is given to us. It's when x is bigger than or equal to 0, and the range we can figure out just by looking at this graph. We can see that it goes up forever, but we can see that it has a minimum here at 2. So therefore the range is when f of x is bigger than or equal to 2. It could also be equal to 2 because it could be equal to 0, and at this point of 0 it is 2. It doesn't have an upper limit for the range because this just goes up forever and ever and ever when x increases. But this is the range when f of x is bigger than or equal to 2. So therefore for the inverse f of minus 1 of x, the domain would be the range of f of x. So this would be when x is bigger than or equal to 2, and then the range would be the domain of f of x, where f of minus 1 of x is bigger than or equal to 0. And then this is the final answer, where the inverse is equal to the square root of x minus 2 over 3, and this is the domain and range. Another feature of inverses is the graph f of the minus 1 of x is the graph f of x mirrored in the line y is equal to x. So this is the example we talked about at the start, where f of x is equal to 5x minus 4, and this is it sketched here. And the inverse f of minus 1 of x is equal to x plus 4 over 5, and its sketch will be f of x reflected in the line y is equal to x, which is the straight line here that is right between the x-axis and the y-axis, like this. So the graph will be, so it'll be reflected here like this, and then it will be reflected here like that as well. And the points of intersection with the coordinate axis will also be mirrored. So the root of y is equal to f of x is 4 over 5. So this here, which is the y-intercept, will be 4 over 5 here because they're mirrored. This point of intersection here is mirrored to here, and the same here. This point of intersection here is mirrored to here in this line. So this is minus 4, so this here is going to be minus 4 as well. So this root is minus 4, and this is the graph y is equal to f of minus 1 of x. Let's do another example. Let's say that f of x is equal to e to the power of x. Its inverse will therefore be the natural log of x. You can see this very easily if you say that y is equal to e to the power of x, so therefore the natural log of y will be equal to x, so therefore the inverse is the natural log of x, like this. And if we wanted to sketch this, it would be this graph reflected in the line y is equal to x. This starts down here, so therefore the inverse will start down here as it's reflected in the line, and it will look something like this, where it comes up like this here. And then it's like that, where this is the line y is equal to f of minus 1 of x, where it's reflected in the line like this. This here is 1, so therefore this here will be 1 as well. It will just be intercept of the x-axis as well. We already talked about this in the laws of logarithm and logarithm equations video. I just wanted to mention it quickly again. So here's the other example that we did. F of x is equal to 3x squared plus 2, and we saw that the inverse is equal to the root of x minus 2 over 3, like this. And if we wanted to sketch this, it would be this graph reflected in the line y is equal to x. So this starts from here, so this will start somewhere down here, and this will look something like this here, where this is the line y is equal to f of the minus 1 of x. This here is 2, so therefore this here will also be 2, like this. Now, you may have noticed that we have specifically made the domain when x is bigger than or equal to 0, such as there's no graph over here and there's only a graph here. And there's a reason for this. If the domain wasn't this, f of x would become a many-to-one mapping. We discussed this and what this means in the last video more on functions, and for this explanation you need to understand what this means. But with this domain, at the moment it is now a one-to-one mapping. Now normally many-to-one mappings are completely fine and we don't need to have this domain, but we have this domain here because we have made the inverse here. If this domain wasn't here, then this would now become a many-to-one mapping, and it would look something like this, where this would come up like this as well, like this. And as a result, as we're reflecting this, this graph would have the same, so it would come down like this, and the reflection would be continued. But now we have a problem, because the inverse is now a one-to-many mapping. One x value is giving off multiple y values. We discussed this on the more on functions video, but we cannot have this because f of minus 1 of x would no longer be a function. So normally we don't have this domain, but as we want the inverse to exist, we have to have this domain here, such as this part of the graph doesn't exist, and such this part of the inverse graph doesn't exist either. Again, go back to the more on functions video if you need to understand better how functions work, but when we want the inverse to exist, we need this domain here. So here's an example question involving inverses and finding an inverse. So for part A, we need to find the range of f of x, and f of x is a quadratic. So if you look at what a quadratic looks like, this is a positive quadratic. Remember, it has a positive coefficient. That it has no upper range because this just keeps going up forever and ever, but it does have a lower range at this minimum point here. So if we find this minimum point, check that it does lie in this domain for when x is bigger than or equal to 1, and then find the y value, this will be the lower bound range of f of x. And the easiest way to do this, in my opinion, is to do differentiation and find the stationary point. So we can do that f dash of x is equal to, so x squared differentiated is going to be 2x, and then minus 2x differentiated is going to be minus 2. So therefore f dash of x is equal to 2x minus 2. And then to find a stationary point, you equal this to 0. So therefore it's going to be 2x is equal to 2. So therefore x is equal to 1. And this does lie in this domain because x can be bigger than or equal to 1. So this is going to be where the x coordinate for where the minimum point is. So therefore the y coordinate is just going to be when we sub 1 into this. So it's going to be f of 1 is equal to 1 squared minus 2 1 minus 15, which is equal to 1 minus 2 minus 15, which is equal to 1 minus 17, which is equal to minus 16. So this is the lowest point that f of x can be because it's a stationary point. So therefore the range of f of x is when f of x is bigger than or equal to minus 16. And this is the range, and this is the final answer. So for part B, we need to find the inverse of f of x. And initially, this looks quite hard. There doesn't seem to be a clear way to do it. And the reason is because there's a very obscure method that you have to do that you should learn for questions like this. And it's completing the square. Completing the square comes up all the time at A level. I've done a video on it before. Really learn how to do it because it is really useful and comes up all the time. So what we're going to do first is replace this with y. So this is going to be y is equal to x squared minus 2x minus 15, and then we're going to bring the minus 15 on the other side to do y plus 15 is equal to x squared minus 2x, and then we can complete the square on this side, so it's going to be y plus 15 is equal to, and then remember we half this coefficient here, so it becomes x minus 1 squared, and then this is going to produce minus 1 squared, which is 1, so we need to minus 1 to make sure that when this is produced by the bracket, this gets taken away. Move the minus 1 onto the other side to get y plus 16 is equal to the x minus 1 squared, and then square root both sides to get the square roots of y plus 16 is equal to x minus 1. This is not going to be plus or minus for the same reason that we talked about before with quadratics, because then that would become a one-to-many function. And then move the 1 onto the other side to get that the square root of y plus 16 plus 1, the plus 1 is outside the square root, is equal to x. So therefore, f of minus 1 of x is equal to, if we replace y with x, so it's going to be the square root of x plus 16 plus 1, like this. And this is the final answer, but we also need to state its domain and range. We know the range because we talked about it before, and the domain is told here. So remember that for f of minus 1 of x, it flips around the domain and range. We said that at the start. So the domain would be the range of f of x, which we figured out to be this. So the domain would be when x is bigger than or equal to minus 16, and then the range would be the domain of f of x, which is when x is bigger than or equal to 1, so therefore the range is f minus 1 of x is bigger than or equal to 1. So for part C, we need to sketch f of x and f minus 1 of x, and the technique to this is just to sketch f of x, which is a quadratic, we know how to do that, and then reflect it in the line y is equal to x in order to sketch f minus 1 of x. So the technique for this is just to sketch this first, f of x, which is a quadratic, and it can be factorized to x minus 5 x plus 3, so therefore it has its roots at 5 and minus 3, has a y-intercept of minus 15, and is a positive quadratic. So this is the graph of x squared minus 2x minus 15, but is not the graph of f of x because this is only in this domain here. So if we say that x is equal to 1 is about here, therefore this graph will only be this segment here. This is the graph y is equal to f of x and doesn't include the green parts here, it's just the red parts where it has a root of 5. And now we need to sketch a graph of f of minus 1 of x, and this will just be a reflection in y is equal to x. So firstly, let's sketch y is equal to x. So this is the line y is equal to x, so therefore this graph will have to be reflected in this graph, and as this starts from somewhere down here, it will be somewhere like this. Don't include the green part that I just deleted, as that's not included in f of x, and we're reflecting only f of x. So if we reflect it, this part up here will look something like this, and then this will come down like this here, meet the y-axis here, and then come down to here like this, where this here will be where it ends. This y-intercept, as this is 5, this is also going to be 5, and therefore this is going to be the graph y is equal to f of minus 1 of x, where you've reflected this line in the line y is equal to x. And then for part D, we need to solve the equation f minus 1 of x is equal to 2, so therefore it's going to be when the root of x plus 16 plus 1 is equal to 2. Move the 1 onto the other side to get the root of x plus 16 is equal to 1, and then square both sides to get x plus 16 is equal to 1 squared, which is just 1, so therefore x is equal to minus 15. Check this lies in the domain. X has to be bigger than or equal to minus 16, and minus 15 is bigger than minus 16, so therefore this is a valid solution. So here's a question on composite and inverse functions. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for part A, we need to write down the range of f, and we're told that f has the domain minus 2 to 6. So these points here, minus 2 to 6, this is the whole graph. It doesn't like go on further or anything like that. This is it. And therefore from this, it's really easy to find the range. The lowest point is here, and this is where it lies on the x-axis, so this is when it's going to be equal to 0, and then the greatest point is all the way up here when it tells us that it's equal to 10, and it says it up here as well. So therefore the range is going to be the lowest point is 0, and the greatest point is 10, and we're told that the domain can also equal these values as well, minus 2 and 6, so therefore we need to put the equals inequality signs as well, and that's the final answer. So for part B, we need to find f of 0, and this originally looks quite hard because we don't know what the function f of x is. So how are we meant to figure out the composite function f of x and then sub in 0 in order to get the value? And the reason is because this is not the technique or the method that you've got to use to do it. So this is f of 0, and I want to remind you of something that we did at the start, that another way we can write this is f of 0, like this. So this is f of x, but instead of x we've got f of 0, and this is useful because we can find the value of f of 0 from this graph here. So this is when x is equal to 0, so this is going to be f of 0, and we can figure this out. You can either figure this out by finding the equation of this line here and then doing it by that. Another way you can do it is realizing that this point here is minus 2, 10, and this point here is 2, 0. So this lies halfway between the x coordinates minus 2 and 2, so therefore it has to lie halfway between the y coordinates 10 and 0, so therefore this point here has to be 5. So you can figure out that f of 0 is equal to 5. So therefore f of 0 is equal to f of 5. And then we can use the exact same technique. We can figure out what f of 5 is by using this diagram. So this is 2, so this is 3, and this is 4, and this is 5. So this is f of 5 here. You could use the same thing and find the equation of this line and figure it out by that, using that. But another way that you could do it is realizing that this is 2, 0, and it says here that this is 6, 4, and then this is just going to be a progression 1, 2, 3, like this. So this is 3, 1, this is 4, 2, and therefore this is 5, 3. So therefore f of 5 is equal to 3. And this is the final answer. f of 0 is equal to 3. So I've seen a couple of past exam questions worded like this. So just remember that you can word a composite function or write a composite function like this, where we can find the value of this constant and then plug this into the graph in order to get out a value. So for part C, remember that this here just means g of x, so you can kind of it's just another way of saying it. It's just g of x is equal to this, and we need to find the inverse g of minus 1 of x. So the first step, again, is, as we talked about before, is to replace this with y, so it's going to be y is equal to 4 plus 3x over 5 minus x, and then we're going to times everything by 5 minus x to get rid of the denominator, so it's going to be y of 5 minus x is equal to 4 plus 3x, and then expand the bracket to 5y minus xy is equal to 4 plus 3x. And I'm going to put all the x terms on one side, so I'm going to move this onto the other side to do 5y minus xy minus 3x is equal to 4, and then move the 5y onto the other side to do minus xy minus 3x is equal to 4 minus 5y, and then I'm going to factor x out of all of this, so it's going to become x of minus y minus 3 is equal to 4 minus 5y, and then divide both sides by minus y minus 3 to get x is equal to 4 minus 5y over minus y minus 3. I'm going to times both the numerator and the denominator by minus 1 as well, because this is kind of like a bit of like an unneat way of writing it. So therefore x is equal to 5y minus 4 over y plus 3. And then the last step is we just replace all of the x values with y. So it's going to be 5x minus 4 over x plus 3, and then this is what g of minus 1 is equal to. G of minus 1 of x is equal to 5x minus 4 over x plus 3, and that's the final answer. So for part D, we need to solve the equation g f of x is equal to 16. Now again, this looks quite hard because we don't actually know what f of x is. So how do we do this? And the reason is because we have to approach this a different way. Recall from what I said about inverses, one of the property of inverses is if we have the composite function g of minus 1 of x, which is also equal to g minus 1 of g of x, this is equal to, and the kind of the functions cancel out, and whatever is left in the bracket is the answer. So in this case it's going to be x. So if what was in the function was something else, it would be equal to this. So for this equation g f of x is equal to 16, we're going to take the composite function of both sides of g minus 1 of x. So it's going to be g minus 1 of g f of x, and this is equal to g minus 1 of 16. This is still a valid equation because we've done the same to both sides. We've done g minus 1 of both sides. And this here, we have this feature here. An easier way to write it might be g minus 1 g of f of x is equal to g minus 1 16, and we have this here that will cancel out and leave whatever is left in the bracket, which is f of x. So this is going to be f of x is equal to g to the minus 1 of 16, and we can figure out g minus 1 of 16 because we can just plug it into here, and we have the graph of f of x, so whatever we get out we can just see when it equals this. So let's do this. So first of all, let's figure out g minus 1 of 16, which is going to be equal to, so we plug it into here, so it's going to be 5 of 16 minus 4 is over 3 plus 16, which is going to be equal to 80 minus 4 over 19, which is going to be equal to 76 over 19, which is going to be equal to 4. So therefore f of x is equal to 4. Now we are told that this point here is 6, 4, so we'll say that y is equal to 4 is about here. And we can see that there are 2 points for which f of x is equal to 4. One here, but there is also one here as well. This is when f of x is equal to 4. So what are these 2 points? Well, this one here is easy because this here, as we just found out before, is 6. So therefore x can be equal to 6. And then to find this point here, we actually need to find the equation of this line, which isn't too bad because we know 2 points on the line, 2, 0, and this is minus 2, 10, and we know that this is the y-intercept, and we figured out in the first question that this is equal to 5. So therefore we can figure out the gradient because the gradient is equal to y2 minus y1 over x2 minus x1. We have 2 points. This is going to be 0 minus 10 over 2 minus minus 2, which is equal to minus 10 over 4, which is equal to minus 5 over 2. And then c is equal to 5, as we figured out before. So the equation of the line is y is equal to minus 5 over 2x plus 5. And we know that y is equal to 4, because this is y is equal to 4, the line. So therefore, this is going to be 4 is equal to minus 5 over 2x plus 5, and then we just figure out x. So it's going to be minus 1 is equal to minus 5 over 2x, so therefore x is equal to minus 1 divided by minus 5 over 2, which you figure it out and put it to a calculator, is equal to 2 over 5. So x is equal to 2 over 5, so there are two values of x. X is equal to 6, which is here, or x is equal to 2 over 5, which is here. And that's the final answer.